I am thrilled to extend a warm welcome to everyone joining us this evening for Stories of the Water Cycle. I'm your host, Nicole Feltz. I'm a science communicator in USGS's water mission area, and I am so happy that you're here joining us for the release of the new water cycle diagram. All right, I think my camera is a little bit blurry right now. I want you to know that this meeting is being recorded. First, let's walk through how we're going to tell the stories of the water cycle during this release party. First, we will hear opening remarks from the U.S. Department of Interior Assistant Secretary for Water and Science, Tanya Trujillo. Throughout the evening, we'll have a few opportunities for live audience interaction through our live polls. Drippy, our friendly water droplet, will share the journey through the many cycles of water, visiting many different USGS scientists along the way who will give us lightning talks on their science. Then we'll dive behind the scenes with Haley and Rachel to learn about how to interpret and use this new tool and how the diagram was made and why. After all our panelists present, we'll have the opportunity to ask them our burning questions in the live Q&A session. Throughout this evening's party, you'll have the opportunity to enter our raffle. We're giving away 5 poster copies of the new diagram. Enter our raffle by visiting the link that will be in the chat momentarily or scanning the QR code on the screen. Finally, during our closing ceremonies, we will announce the raffle winners. And again, this meeting is being recorded. I am so pleased to welcome our special guest, Tanya Trujillo, to this event. She is the Assistant Secretary for Water and Science in the U.S. Department of the Interior. Tanya is a water lawyer with more than 20 years of experience working on complex natural resources management issues and interstate and transboundary water agreements. Thank you, Tanya, for opening this special event.
Hello, everyone. Thank you very much for having me. I am super excited to be here with the incredible team from USGS that's put together a really fun program for us. I am the Assistant Secretary for Water and Science. I have the great pleasure of being able to work closely on a day-to-day basis with an incredible team of scientists from USGS and from the Bureau of Reclamation at the Department of the Interior. We have a great team together, and we emphasize the collaboration that enables us to do our jobs as much as we can. USGS in particular collects vast amounts of water data, as many of you know, and in recent decades that has been able to contribute to many different professions, many perspectives of our daily life. Myself as a water lawyer rely on this basic data for my entire career, and the new exciting developments that we have, or the show that we're going to be emphasizing today with respect to the water cycle diagram, is really exciting. It helps us communicate our science and the information that we have to a broad of audience as possible. The USGS scientists have made key contributions to our understanding of how surface water and groundwater interact, and they have also helped us evaluate water quality and water quantity issues in many different contexts. The USGS scientists are leaders and innovators in the field of water resources, and they provide the scientific foundation for the work that we do across the Department of the Interior and also across many of our other federal agencies. And I know many of the non-federal partners rely on USGS science, again, on a daily basis for all of their work, whether it be policymakers, legal practitioners, land managers, many different types of entities rely on our basic science. So thank you, especially to all of the folks who put together this program, but who are operating in their capacities on a day-to-day basis. I have been able to utilize the data in my career. I know the prior version of this water cycle diagram has been translated into over 60 languages and has been reprinted in thousands of textbooks and diagrams and posters all around the world. The value of the water cycle diagram is unsurpassed as far as helping us communicate our impacts on the water cycle, on how we have our actions have a direct implication to how water is managed around the planet. The new diagram emphasizes that human activities element much more, and it helps us understand how the natural phenomena are influenced and supplemented by our actions. The timeliness of the diagram will speak for itself. We know we have to clearly communicate and understand the role that we play in that changing environment with respect to the water cycle from top to bottom of all of its various uses. So I'm looking forward to hearing the presentations, to hearing the stories that we have put together for us today. I really want to compliment the team at USGS for their ongoing efforts, and I hope that the audience who's participating today will help us continue to improve upon our tools and think about the relationship between the water cycle and our actions in all of our day-to-day activities. So thank you all very much. Thank you to the team at Interior and at USGS, and turn it back to you, Nicole, or whoever else is next. Thanks a lot.
Thank you so much, Assistant Secretary Trujillo. Next up, we'll hear from Emily Reed, USGS Web Communications Branch Chief, about our motivation to redesign the diagram. But before we do, let's find out who's in the audience today. Where are you joining from? In which state do you live? You can join this live poll by going to slido.com and using the code USGS. You can click the link that will be in the chat momentarily, or you can scan the QR code on your screen. Once responses start coming in, we'll see them live. So let us know. Where are you joining from? While the responses come in, I'll let you know where I'm from. I am in Maryland, just outside of Baltimore. Minnesota, Virginia, Texas. Some more Maryland, Michigan, disproportionately representing Maryland. This is quite excellent. Georgia, California, Indiana, New York, Wisconsin, West Virginia. This is looking pretty cool. Thanks for participating, folks. I love how it changes live straight away. Alaska, other places in California, Iowa. Did I see Colorado? Oregon, Connecticut, PA. Wow, I have to say, we are really repping the whole country here, folks. This is pretty neat. Awesome. So cool. Well, we're so happy to have people join from all over the place because the water cycle diagram is global. Arizona. Cool. And I see some water science centers too. Florida, Idaho. Great. Well, thanks, folks. You can keep participating in that live poll. And we're going to go ahead and move on, and we are going to hear from Emily Reed, Chief of the Web Communications Branch within Water Resources Mission Area. Emily?
Thanks, Nicole. Today we're celebrating the release of a brand new USGS water cycle diagram. You may already be familiar with the current USGS water cycle diagram. It was first published in the year 2000 by Howard Perlman and John Evans, and it's been translated into more than 60 languages. It's among USGS's most popular plain language science resource, and it's accessed by hundreds of thousands of educators, students, and global community members every year. The current USGS water cycle diagram is one of many educational resources available in the USGS Water Science School, a website that provides approachable information about water for instructors, K-12 students, parents, and more. More than 8 million users visit the website annually, with a third of all traffic on pages and resources related to the water cycle. On the website, we have a plain language description of the global water cycle, photos, interactive activities, as well as water cycle diagrams, including one for elementary learners, and our current diagram for middle schoolers and beyond. Visuals like the current USGS water cycle diagram play a key role in the communication and comprehension of science. They're directly related to how audiences engage with, remember, and identify with a topic or body of work. Compared to text alone, visuals make it easier and more efficient for our brains to process information. They can be more engaging and attract broader audiences by being visually appealing or relatable. Educators, policymakers, other professionals, and maybe even you use the USGS water cycle diagram. It serves as the single resource that many individuals rely on for their entire knowledge of the hydrologic cycle. Public perception of water movement, quality, quantity, and availability are shaped by diagrams like ours. So it's important that this kind of tool is done right. Since the USGS first published the current water cycle diagram in 2000, water science and our understanding of the water cycle have evolved. For example, we better understand the connectivity and interactions between groundwater and surface water. In addition, increasing environmental change and major issues like drought, flooding, and other natural hazards have emphasized the role of humans in the water cycle. Much of this important information is not represented in the current version of the diagram, providing an incomplete picture of the water cycle. This discrepancy between water cycle science and water cycle depictions is not unique to the USGS diagram. A team of university researchers led by Ben Abbott from Brigham Young University in Utah did a study of water cycle diagrams in 2019. They analyzed the contents of more than 400 water cycle diagrams around the world, including the USGS diagram. In their study, they found that 85% of the diagrams they studied showed no interaction between humans and the water cycle. In addition, 95% of diagrams focused exclusively on a single watershed, which ignores important water movement that occurs between watersheds or over long distances. And most diagrams omit or underrepresent major water pools on Earth or places where water is stored. For example, 50% of the diagrams underrepresent or omit 5 of the 10 largest global water pools. Those are non-renewable groundwater, permafrost, saline lakes, wetlands, and soil moisture. Most diagrams also omit or underrepresent major fluxes of water or processes that move water from place to place. For example, 92% of the diagrams omit the largest global water flux, which is ocean circulation. We understand the importance of supplying this key communication tool. That's why we've redesigned the USGS water cycle diagram. It is functional, aesthetically pleasing, and informed by the most rigorous science. I can't wait for you to see the new diagram later in this event.
Thank you, Emily. It's really helpful to understand why we created a new diagram. I can't believe it's been over 2 decades since the previous diagram was created. Let's do another live poll. You can join us by going to slido.com and using the code USGS. You can scan the QR code on the screen, or you can click the link that will be in the chat momentarily. The question that we're asking is, have you used any USGS educational resources? And if so, which ones have you used? Of course, we're well known for our maps, so that makes sense. That's a good answer. I wonder what specific maps you've used. Maybe so many you can't even list them. The water cycle. Well, that's great to hear. I'm glad you're here. Yeah, we definitely offer a lot of raw data. Diagram, of course. More maps. stream gauges, rainfall gauges, gauge data, live earthquake map. Did you guys know that there was an earthquake in Maryland? Like, what was that, yesterday? Couldn't believe it. Stream stats, glossary, more of the water cycle, the water science school, where the water cycle diagram is hosted. Yes, of course. Maps, the water cycle, water models, activities from the Youth and Education and Science Office. Yes. Water cycle maps, live earthquakes. This is great. I love all these answers coming in. Yeah, topographic maps. Adventures in STEM, other water resources, GIS layers. NWIS. National Water Information System, which is now water data for the nation. Great. This is awesome. Thank you so much for everyone who's responding to this poll. You can continue responding, and I'm going to orient you to the next spot in our journey. This is the fun part. Let's join Drippy for their journey through the many cycles of water. But before we do, don't forget to enter our raffle for your chance to win a poster of the new diagram. We'll be selecting 5 random winners at the end of this evening's party. So, who is Drippy? Drippy is our friendly water droplet, our water science school mascot and educator. Drippy is our guide for learning about all things related to water. Let's join Drippy on their adventure through the many cycles of water. Together, we'll travel from a mountaintop to the ocean and many places, many pools and fluxes in between. Let the journey begin. Clouds gather over a mountain, threatening snow. As the precipitation begins to fall, a single snowflake stands out. Drippy, our friendly USGS water droplet, falls on the mountaintop, forming a fresh new layer of snow on top of the seasonal snowpack. Snow and ice accumulate, piling on top of Drippy, burying them deep in the snow. Now stored within a frozen water tower, Drippy rests in their frozen form throughout winter and into spring. Temperatures rise as spring turns to summer, transforming Drippy from their solid form of snowpack into their liquid form, snowmelt. All right, and now we will hear from Andy Creighton, a USGS hydrologist with the Colorado Water Science Center, where her research focuses on geophysics and alpine snowpack dynamics. Andy, take it away.
Thank you. All right, as snow falls and accumulates at high elevation throughout the winter, it creates what is called snowpack. Snowpack persists throughout the winter until the arrival of warmer weather when it begins to melt, becoming snowmelt. But snowpack dynamics are complicated. So USGS scientists and I are trying to better understand snowpack and how it melts, and what that means for water users throughout the year. You might think since snow is made of water, the same depth of snow would contain the same amount of liquid water. But the type of snow matters. How much liquid water do you think would be in 3 feet of snow? Like 3 feet? I'm short, so 3 feet, right? Do you think it would be different for 3 feet of fresh, dry, fluffy snow versus 3 feet of compacted, wet, slushy spring snow? It can be different. So we have a measurement called snow water equivalent that represents the amount of water stored within the snow. 3 feet of fresh, dry, fluffy snow may represent only 4 to 5 inches of snow water equivalent, while 3 feet of compacted, wet spring snow may contain 12 inches or more of snow water equivalent. This is why, as hydrologists, we're more interested in the amount of water stored within the snow than its depth, since that's going to melt and create our water supply. One way we measure snow water equivalent is by using a snow sampler. It's a tube that was invented in the early 1900s, and we're still using the same technology today. We insert the tube into the snow, And then we pull it up and we weigh the snow using our handy dandy mixing bowl and scale to convert it from weight into the inches of water. We also dig snow pits to gather in-depth information about each snow layer's depth, density, and also its stability. We use a probe, which is basically a fancy ruler, to measure snow depths across transects. We then use those depths to estimate the snow water equivalent across a larger area. But these measurements only give us a snapshot of the snow at only specific locations, at only one time, and are often limited in number due to how long these measurements can take. Let me tell you, digging these snow pits can take hours sometimes. Fortunately, we're incorporating existing technologies to create new sampling methods for our field. We're using sled-based ground-penetrating radar to measure snow depth and density across larger areas than probes or pits could survey, and this allows us to measure wider areas of snow faster, in more detail, and with greater accuracy. We're also leveraging drone technologies, including methods such as LiDAR and airborne software-defined radar to make measurements across even larger areas of the mountain. Drones allow us to survey locations that are too dangerous for people, like in avalanche zones. It's important for us to have high-quality data collection methods because snowpacks are fundamentally changing due to climate change. This can impact water availability all year long. So let's talk about a typical snowpack. Typically, around October, snow begins to fall and accumulate. Especially at high elevations, the snowpack can be several feet thick and store several inches of snow water equivalent. In this graphic, this is a typical amount of snowpack. In early summer, when snowpack melts, the liquid water races downhill, recharging the stream with lots of water. There's often a peak of maximum stream flow during this time. That stream flow can be captured by downstream diversions or in reservoirs. For many places in the western U.S., spring snowmelt comprises the majority of the annual water budget. But let's compare that to a low snow year, which is more common now due to climate change. Climate change can mean less snow accumulation, warmer winters, and earlier springs. Climate change is influencing when and for how long the snowpack melts. Liquid water is released earlier and slower than it would be prior to climate change influences. There may not be a spring streamflow peak like there would be in a typical season. Summer streamflow will be low, and downstream reservoirs may only receive a fraction of their usual water budget. So our work, which sheds light on the whole system, is crucial for everyone who relies on snow for their water. And you don't have to live in the mountains to receive your water from the snowpack. Water in the deserts of California, like Los Angeles, and in the agricultural fields of Kansas can come from the mountain snowpack due to trans-mountain water diversions and reservoir systems. Approximately 2 billion people are expected to experience diminished water supplies because of seasonal snowpack decline this century. Over the last half century alone, particularly in some regions of the western U.S., annual snowpack levels have declined and contributed to reduced streamflow. Every drippy drop counts when the stakes are this high and this many people depend on our snow resources. USGS scientists are working diligently to not only measure snowpack in established ways, but also to find innovative ways to measure it faster, safer, and with greater accuracy.
Drippy wanders lazily down through the snowpack, slowly infiltrating into the soil below to join shallow groundwater. Percolating down through the ground into shallow groundwater, it doesn't take long for Drippy to emerge from beneath the soil along the wooded banks of a headwater stream. Surrounding Drippy are countless organisms which inhabit the cold waters of the stream. Drippy is pulled farther downhill by gravity. Deposited suddenly into rapidly moving water, Drippy is ushered into a larger river headed for a reservoir at the base of the mountain. Cooling into the reservoir, Drippy rests easy with friends for months in the cool depths until they are needed downstream. And now we'll hear from Marty Briggs, a research hydrologist with the USGS Water Mission Area Hydrologic Remote Sensing Branch. Marty specializes in understanding how groundwater and surface waters are connected and how groundwater influences stream water quality and habitat resilience. Marty, take it away.
All right, hello. Most of the stream length across North America is actually found draining highlands such as hills and mountains, and they're called headwater streams. This cartoon graphic of the Neversink Reservoir watershed in the mountains of New York depicts how water can move on the land surface and underground to form headwater streams, which in turn join together to form larger rivers at lower elevations. Rain across the headwaters that is not taken up directly by vegetation or surface evaporation runs off into stream channels or percolates downward into the soil, recharging both shallow and deep groundwater. After a short trip underground, shallow groundwater can emerge quickly in springs and seeps, or instead travel deeper and longer flow paths into bedrock layers. These geologic differences impact stream temperature and where cold water loving fish, such as trout and salmon, can survive on hot summer days. As Andy discussed, precipitation that falls in winter can stack up as snow and ice on the land surface. And as that snowpack melts, cold water can run off into local streams and also recharge groundwater, helping to create the local aquifer. During dry times in summer, headwater streams are often mainly supported by groundwater discharge out of soil and rocks, and that water moves downhill toward larger rivers, lakes, and reservoirs. Our understanding of the water cycle includes that water can reside underground for a matter of days to many thousands of years, and we interpret this time as the average age of groundwater. Even near the tops of mountains, groundwater that drains to streams can be surprisingly old. This picture shows USGS scientists using heat-sensitive cables to locate groundwater discharge zones in western Colorado, so that water can be directly sampled for contamination from gold mining that occurred in the late 1800s. Groundwater seeps and springs are often tucked underneath roots and rocks along headwater streams. This image shows a University of Connecticut graduate student collecting water from a groundwater spring emerging below a stream bank tree. That water will be analyzed in USGS laboratories to check for signs of excess fertilizer and other contaminants to evaluate how long the water has been flowing underground. The age of the groundwater discharge indicates whether it is coming from local hill slopes or deeper bedrock, which in turn impacts stream temperature and water quality. Have you ever felt a cold spot on your toes when walking in a stream or pond in summer? That may have been groundwater discharge. By using thermal infrared cameras, scientists can visualize cold groundwater discharge points in summer while walking down streams or floating in kayaks. Here you can see a zoomed in photograph of the tree roots and a thermal image overlaid in the middle, capturing the dark blue groundwater discharge that trickles into the adjacent river and heads toward a downstream reservoir. This helpful heat sensing technology is greatly improving the spatial coverage of groundwater discharge surveys in headwater streams, leading to new scientific understanding of the water cycle. As shown in this photo, headwater streams in the Neversink Reservoir watershed drain a complex landscape of exposed bedrock and coarse, rocky sediments. These streams are home to the beautiful brook trout, which can use groundwater discharge zones for staying cool in summer and growing their eggs in winter. Other organisms like bugs you can see with the naked eye, called macroinvertebrates, indicate to scientists how healthy the stream is. The Neversink River is considered the birthplace of fly fishing in America, but the trout there can be stressed by low stream flows and warm temperatures caused by climate change. Groundwater discharge protects streams against those changes, helping fish such as brook trout and other stream organisms survive. The USGS Next Generation Water Observing System program has deployed instrumentation throughout the Neversink Reservoir watershed to evaluate how headwater streams and groundwater are connected. Drainage from groundwater helps to fill the Neversink Reservoir, shown here with USGS monitoring equipment along the dam. The reservoir holds 34.9 billion gallons of water and provides an important water supply to New York City. That is a lot of Drippies. So next time you visit Times Square, take a drink from a public water fountain and think about the importance of headwater streams in the larger water cycle.
Released from the reservoir, Drippy continues the downstream river journey. Upon nearing an urban area, Drippy is sucked out of the river and into a thermoelectric power plant. Its cooling system warms up Drippy, then flushes them back into the river to continue flowing towards the city. The city's infrastructure redirects the river water for municipal water use, sending Drippy into someone's home. A child turns on the kitchen tap, filling a glass of water and carrying it outside before taking a sip. Drippy narrowly misses the complex internal world of the child, instead evaporating from the glass and floating into the atmosphere as invisible water vapor. Drippy joins a cloud, then is released in a raindrop over the city. Hitting a rooftop, Drippy slides rapidly down through the gutters and spouts, shooting out onto the sidewalk. Surrounded by a growing water droplet community, Drippy becomes part of a rapid sheet flow. The water glides over the hard, impervious surfaces of the cityscape, collecting all sorts of things as Drippy flows down the street and into a storm drain. Chemicals, sediment, and other gunk from the surface join Drippy on the journey through the underground drain system until Drippy and their friends gush out of a pipe and into the ocean. Having been pulled by gravity into the largest pool of water on the planet, Drippy is ready to rest easy, but a storm surge suddenly raises the ocean level. Drippy is sent hurtling towards the city shoreline. Floodwaters race along the streets, damaging buildings and vehicles near the shore. But thanks to a recent project that installed green infrastructure, Drippy comes to rest in a low-lying stormwater retention pond before doing any more damage. Drippy is taken up by the roots of marsh plants, then transpired from their leaves under the warmth of the sun. Drippy leaves behind the hitchhiker chemicals and sediment that were carried along in the storm surge. And now we'll hear from Jon Dillow and Marina Metes, USGS scientists from the Maryland, Delaware, DC Water Science Center. Jon is currently the surface water specialist for the Maryland, Delaware, DC Water Science Center, one of the many roles he has filled during his 30-plus year career with the USGS in Maryland. Marina is a physical scientist at the same Water Science Center. She studies fluvial geomorphology and remote sensing, particularly within the Chesapeake Bay watershed. Jon, take it away.
Thanks, Nicole. And hi, everybody. One of Drippy's many urban adventures over the years happened in Ellicott City, Maryland back in 2018. Ellicott City has a watershed that's a little under 4 square miles. It's about 65% developed and 27% forested. It has at least 15% of the basin where the surface is covered by roads, parking lots, driveways, and rooftops, which makes it impervious. Traditional stormwater management is focused on getting precipitation that falls on the ground into the drainage channels and out of the watershed as quickly as possible. Here's a stream channel in an urban environment. It's very straight, which is not natural. It has a lot of rocks and cobbles on the bed and a stone wall on one side, and it's very constrained. In short, it's engineered to make the water move downstream as quickly as possible. But as we can see, with larger and more intense rainfalls associated with changing climate and increases in impervious area due to watershed development over time, traditional stormwater management approaches are increasingly ineffective at preventing flooding. In this example, the channel can carry the water for a while, but as more water is added, eventually the water comes up out of the channel, and now we have flooding. Now, we've all heard the warning, turn around, don't drown. And we know what that means. It means stay away from the force and velocity of flowing floodwaters. Here we can see an example of what can happen during a flood. In addition to a lot of water going where it isn't wanted, other things can get carried along downstream. Big things like trash dumpsters, and even some cars coming down from above there. Eventually, we end up with a lot of cars and other debris and we have water going out all over the place, well beyond the original channel. Now, when too much water runs off too quickly and 2 or more drainage channels come together, the results can be catastrophic. The channel that we just saw on the previous slides was one of 3 major channels that converge in Old Ellicott City. In that same flood event, when Drippy and all their friends got into those channels and all came down at once, we can see what eventually happened on Main Street. We start with some water in the gutter, which is where we want it to be. But then a little more water arrives. And then too much water arrives all at once, and we have cars starting to float and get pushed downstream by the floodwaters. And eventually, it just creates one big mess. And we can see here that in addition to the force and velocity of the water carrying things away, the water is high enough to get in the doors and first floor windows of these buildings, ruining anything inside that gets submerged. But all this destruction is only half the story. Here's a forested section of one of those 3 drainage channels, and we can see the aftermath of flowing floodwaters here. It's important to understand that in addition to the flood damage, all the water that's running off so quickly ends up leaving the watershed without recharging local groundwater levels or even giving the local ecosystem a chance to benefit. So urban watersheds actually end up losing twice, both during and after a flood. Now, fortunately, there are some new approaches to urban stormwater management that can produce much better results.
Newer stormwater management practices, which are referred to by a variety of names such as green infrastructure, low impact development, distributed stormwater management, or best management practices, are starting to be implemented in urban and suburban areas. This type of stormwater management often includes smaller stormwater features dispersed in many locations across the landscape to better manage stormwater closer to where runoff begins. In these types of systems, stormwater is diverted from impervious surfaces such as roads, driveways, and rooftops, and flows through a series of stormwater structures, beginning with features located directly next to impervious surfaces, such as tree box filters or swales, and then to bioretention ponds or dry ponds. These features are intended to absorb some of the stormwater into the ground, which helps replenish groundwater, provide water for vegetation, and improve water quality. These features also help slow the flow and overall volume of runoff that eventually reaches nearby streams, rivers, lakes, and oceans. This helps reduce erosion and control pollution from sediments, nutrients, and other contaminants that are often carried with stormwater runoff. USGS scientists continue to research the effectiveness of this newer form of stormwater management to better protect our natural water resources from urban development. We often partner with local cooperators like state and county agencies. We collect and analyze various data sets on stream flow, groundwater levels, water quality, stream erosion, and the types of insects and fish living in nearby streams. Some of our results show that runoff is reduced during smaller storms, but very intense rain events can still overload these types of stormwater management systems. Some contaminants from runoff are also better controlled than others. For example, we still see an increase in the saltiness of nearby streams due to road salts that are applied in winter. Our research informs how we manage our stormwater, and to learn more about our ongoing research, check out the link in the chat.
As Drippy floats over the town, they feel the excess heat from all the impervious surfaces, driving fellow water droplets to evaporate alongside Drippy. Rising higher and higher into the atmosphere, after some time, Drippy finds themselves precipitating yet again, but this time over an expansive farm field, far to the east of the city. Routed through a diversion canal, Drippy is directed to irrigation for a common crop, corn. The plants grow strong using Drippy before they could be lost yet again to the atmosphere as evaporation. As the corn in which Drippy was last seen reaches maturity, a human harvests a single ear where Drippy now resides. Throwing the ear of corn into a huge bin, the corn and Drippy begin the journey across the country to a processing plant where the corn will be turned into animal feed, continuing the water cycle. And now we'll hear from Kelly Warner, the Deputy Director of Science for the Central Midwest Water Science Center. She manages the water science studies for the USGS in Illinois, Iowa, and Missouri. Kelly, go ahead.
Thanks, Nicole, and welcome, Drippy. Welcome to the agricultural area. Now, water is very important for keeping our fruits, vegetables, and grains growing in the agricultural areas. During the growing season, water gets onto the fields through either precipitation or sometimes through irrigation. Now, irrigation is where the water is pulled either from the ground or the streams, and then it's sprayed onto the fields to help our crops grow. Estimates vary, but about 60% of all the world's withdrawals go towards agricultural uses, such as irrigation. Now, irrigation is really important to understand. So, especially when we're trying to understand our water use and availability in the area, we need to understand irrigation. One of the ways that the USGS studies this type of water use is through satellite imagery. The image on the screen is a satellite image where the red circles are areas of center pivot irrigation. We can see these circles from satellites in space, but you can also see these circles when you're flying in airplanes a distance above the ground. They'll look like big green, brown, or yellow circles on the ground. Now, the USGS can better evaluate how much water is available in agricultural areas by discovering how the water is getting onto the fields and how it is being used. Now, often farmers apply fertilizers to help their fields and crops grow. And you could say it's kind of a party with Drippy and their fertilizer friends, transforming those water molecules as they bind to the fertilizers and other chemicals. For example, in the Midwest, where I live in Illinois, there's a lot of corn and soybean. Can you guess which of the two crops I just mentioned is on the screen? And a hint, it is not corn. Fertilizer often consists of chemicals, nitrate and phosphate, that help our crops grow. So when the water hits the fields after it's been fertilized, then the water, with its chemical buddies, can really seep into the ground. And at the USGS, we monitor how that water and chemicals are transported below the ground. But what influences how fast those chemicals get into the groundwater? Well, it often depends on the type of the soil deposits below the crops. Let's take a look at the graph on the screen. The tall brown bar on the right side of the graph shows nitrate in the water below soils that are made up of very coarse grain deposits. Compare that to the short brown bar on the left side of the graph, which represents nitrate in the fine grain deposits. Now, what this is telling us is that nitrate is higher under areas with coarse grain deposits. So why would nitrate be higher under the area of coarse grain deposits? Well, coarse grain deposits are often where you have that gritty, sandy material that we rub it between your fingers. The particles are big, at least big for soil particles. And the water and chemicals can move through this type of material. They move faster through this type of material. And that makes sense, right? I mean, we have big particles, more space between the particles, and they don't compact as easily. So the water is allowed to flow readily between the particles. Think about that. Think about when you're at the beach and it's very super sandy. The water disappears down into the sand once the wave recedes, right? But when the deposits below the crops are fine-grained, such as clay, then the water and the chemicals move slower. So there's a lot less nitrate that get into the groundwater. And this is important because groundwater is a very common source of drinking water in these rural areas. So it's important for us to understand how the water and the fertilizer interact in the ground. But sometimes Drippy and their buddies, nitrate and phosphate, take that water slide through the tile drains directly to our rivers and streams. Farmers will install these tile drains below our farm fields so that the fields do not flood when there's too much water. Too much water will kill our crops. So the tile drains are like pipes that collect the water under the surface of the ground, and they route that water to a stream or a ditch. You can see the water pipes or tile drains sticking out from the banks of this stream. Now, because the tile drains are close to the land surface, they often contain water that has large amounts of nitrate and phosphate. When the water with the nitrate or phosphate reaches the stream, it can make conditions in the stream primed for algal blooms. Sometimes the algal blooms can become toxic or harmful, which we refer to as harmful algal blooms or HABs. And there's a very complex environment that is needed to form harmful algal blooms. And we do not totally understand the when, why, and where these algal blooms will form or when they'll become toxic. It's a bit of a mystery. But the USGS has lots of studies trying to understand HABs. And this map shows many of those locations where those studies are occurring. So in summary, farmers are very happy when Drippy reaches those agricultural fields because we need water to grow our crops. And the USGS is working very hard to better understand how that water is being used, transported, and transformed in agricultural settings.
Many thanks to the scientists who told us the stories of USGS water science. Now I'll turn it over to Haley, the lead designer of the new diagram. Haley, let's see this thing.
Hello, I'm Haley. I'm the lead designer of the new diagram, and I'm so very, very thrilled to be able to reveal it to you all today. Through Drippy's journey and the science stories, we've heard about many different parts of the water cycle. Drippy moved through snowpack, rivers, the ocean, groundwater, plants, and along the way, they also interacted with human environments and were affected by human actions. You may have already guessed, but all of these little snippets that you've seen over the course of Drippy's journey are part of the revised diagram. The full diagram includes text beneath the illustration and is a 38-inch by 26-inch poster. The full-size version is available today on the Water Science School alongside an 8.5 by 11 version and an 8.5 by 11 fill-in-the-blank version. The diagram and the text beneath it were designed for an 8th grade level to meet US science education standards, but can be used for more advanced students as well. All versions are available in English and in Spanish. Before we dive behind the scenes of the making of the diagram, don't forget to enter our raffle for your chance to win a poster of the new diagram. We'll be selecting 5 random winners at the end of this evening's party. So now we're going to dive behind the scenes. Myself and my colleague Rachel are going to talk a bit about how we designed this new diagram and some of the key improvements. At the beginning of this evening's event, Emily explained that we created a new diagram in order to better represent our current understanding of hydrology and how humans interact with the water cycle. The USGS Water Resources Mission Area convened a team to redesign the diagram to emphasize scientific accuracy, to use effective design, and to be usable in educational settings. This process took 18 months, and many, many individuals contributed to this effort. On the design side, I'd especially like to thank Ellen Bechtel, formerly of USGS, for her early leadership of the design efforts, and Diane Lopez Trujillo with the Caribbean Florida Water Science Center for completing the Spanish translation. Let's first focus on what we did to improve the scientific accuracy of the new diagram. The key scientific improvements that I'm going to highlight here are that we depict human interaction with the cycle, that we depict multiple watersheds, and that we better represent key pools and fluxes. The first step to showing human interaction with the water cycle was, of course, to just show human presence on the landscape. The next step was to show key categories of human water use. We show agricultural irrigation with withdrawals of surface and groundwater. We show grazing water use by grazing livestock. We also show industrial water use including showing a thermoelectric power plant, as thermoelectric power generation alone is the largest category of water use in the US. Finally, we also show municipal and domestic water use, including a water treatment plant. Going one step further, we also show how human water use in turn affects the water cycle. We saw examples of that in Drippy's journey. When Drippy was delayed in the reservoir, we saw how humans can change the timing of when water moves. We often store water in reservoirs for us to use later, for irrigation or for recreation, or simply to stop downstream flooding. When Drippy did move downstream, they got pulled into a thermoelectric power plant. Sometimes our use of water affects the quality of the water. For example, here, Drippy got heated up, which can impair habitat for aquatic species. We can even impact the quality of water without using it directly. When Drippy falls on the city as rain, they end up running off into the ocean because of all the paved, impervious surfaces. And when they do so, they bring all sorts of contaminants with them. Finally, when Drippy is in the agricultural setting, we see how humans change how water moves and how much water is in certain pools. We remove water from rivers and groundwater, and sometimes that use can deplete or contaminate resources like groundwater. The second area of scientific improvement that I'm going to highlight is our depiction of multiple watersheds. From the outset, we felt it was important to visually communicate that the water cycle is not a single big cycle, but is composed of many smaller, nested cycles that are active across the landscape. To that end, we included multiple regions: a coastal plain, a dry endorheic basin or closed basin, a wetter basin with minimal human presence, and an agricultural basin. Each of these basins have their own unique pools and fluxes. For example, the closed basin has a saline lake, and the agricultural basin has a reservoir. But these basins are connected by processes that occur across watersheds and at continental scales, like atmospheric transport of moisture. To emphasize this, we included an inset overview diagram that highlights those broader connections, including transport of moisture from ocean to land and continental moisture recycling. We also improved the scientific accuracy through the depiction of pools and fluxes. We determined which pools and fluxes to include based on peer-reviewed science. We made sure to include key pools and fluxes that are often omitted from other diagrams. Fluxes such as ocean circulation and precipitation over the ocean, and pools such as wetlands, permafrost, soil moisture, and especially groundwater. We intentionally emphasize groundwater as it is a large pool that's hard to understand. Our primary goal was to get away from the narrative that groundwater is an underground river. We wanted to show that groundwater exists in pore spaces of sediment and rock and in cracks in the rock. We also wanted to show that sometimes aquifers have pathways where they can be recharged, and sometimes they are closed off. We also wanted to show human use of groundwater by including wells that are pumping water, hydraulic fracking, and showing how high pumping rates can deplete groundwater or pull saltwater into freshwater aquifers near the coast. So now that we've reviewed the scientific improvements, let's take a look at how we approached designing the diagram. At the outset of the project, we reviewed multiple existing diagrams of the water cycle and of other environmental processes. We were looking at a few things: the use of perspective, the colors, how labels were placed and styled, how arrows were drawn, and how they made use of visual hierarchy. If you're not familiar with that term, the term visual hierarchy is a design principle by which the most important information is designed to be the most visually prominent. It's important because it shapes how users perceive information and how their attention is focused. So what does good visual hierarchy look like? And how is that something that designers can manipulate? To answer that second point first, there are many building blocks that we can use to tweak visual hierarchy. Some of the simplest are size. Here, your eye is drawn to the larger element. We can also use different colors. Here, the red element draws your eye more than the blue. We can also change how intense the color is. Here, your eye is drawn to the brighter purple. And finally, we can change how dark of a color you use. On a light background like this, your eye is drawn to the darker element. We're all familiar with this, probably without realizing it. It's used a lot in text, both online and in print media. And it's also used in website development. You can see how in the right image, the most important features like the button draw your eye immediately, whereas the left image seems visually chaotic. These principles can be used to adjust the design to bring certain elements to the forefront visually and to push others to the back, where your eye won't notice them immediately. It was our awareness of the importance of good visual hierarchy that drew us to landscape architecture diagrams. We are particularly inspired by stormwater diagrams. We love that in these diagrams, the water is the focal feature. It's highlighted in blue, and we also love that the designers chose to show background details in grayscale. Those stormwater diagrams inspired our design aesthetic. Because this diagram is about water first and foremost, and because water is associated with blue, and because blue is a cooler color that gets pushed to the background when paired with other colors, we made blue the only color used. This helps to make the information digestible and easy to follow. Your eye is drawn first to water, just as we want. Then your eye is drawn to the labels, which are paired with the arrows. We use distributed small arrows that keep your eye moving instead of a single big cycle that dominates the diagram. Finally, your eye explores the background landscape and the inset cycle. These elements are drawn in grayscale, which means that they don't draw your eye immediately, but instead are details you can seek out as needed. The design and scientific improvements that I've highlighted here were outcomes of our iterative design process called user-centered design. Rachel is now going to speak more about that approach.
Thanks. So what did we do to ensure our diagram was usable, especially in an educational setting? We spoke with the people who use our current diagram. So this gave us the opportunity to learn how educators teach the water cycle so that we could design the diagram to meet educators' needs. And then throughout that process, we asked educators to give us feedback. And then we took that feedback and incorporated it into our design. Subject matter experts such as USGS hydrologists and over 100 educators from elementary to college level from across the country contributed to this process known as user-centered design. This is an iterative design process where we focus our designs based on the context and the needs of our users. We can learn about our users and how they use our products in order to create solutions that support their needs. Essentially, it's a way to put our users at the center of our activities to improve their experience with our products. Their feedback helped us make strategic decisions about the design of the diagram, including terminology such as streamflow versus discharge, label styles such as using different choices to distinguish pools and fluxes, and plenty of ideas for supporting material. We really appreciate being able to talk to educators and make sure we are meeting their needs. Since we focus on the entire user experience, there are huge benefits to user-centered design. We were able to engage with users and understand their needs, ensure our design met user needs. We were able to balance user needs with stakeholder ideas. We were able to gather ideas for additional resources, and we were able to acquire early user feedback to incorporate into our design. This means we not only thought about our product's utility, so that's like if it provides a feature a user needs, and its usability, how pleasant and easy to use those features are. But we also considered its overall user experience. How do users feel when they interact with us and our products? We strive to create products that meet our user needs by involving them throughout our design process. And as we move forward, we'll continue to involve our users and seek that feedback. We focus on understanding the user's thought process, their feedback, their behaviors, and keep them at the forefront of our minds as we develop, design, and create. So we'd love to start a conversation with you. Get involved by testing our products and providing feedback. So if you're interested in providing 30 minutes to an hour of your time, please email us at our Water Data for the Nation email at wdfn_usabilitytesting@usgs.gov and let us know which products you use. That could be the water cycle diagram or any other Water Data for the Nation product and how you use it, and we'll add you to our product testing roster. I'll pass it back to Nicole.
Thanks, Rachel. And I just want to say thank you so much to Haley and Rachel for your presentations. And thank you, Haley, for revealing the new diagram. That was so interesting to see the behind the scenes of making the diagram. There's obviously so much that went into this, and it's a great way to showcase USGS science. So we dove in deep together into the USGS science that underlies this new educational tool. It's really interesting to hear all of the work that went into this to assure that it was an appropriate tool for educators, one of our primary users of the diagram. Now, don't forget to enter our raffle for your chance to win a poster of the new diagram. As we said, we'll be selecting 5 random winners at the end of this evening's party. Scan the QR code on the screen or click the link in the chat to fill out the raffle form. Let's join one last live poll together before we move into our live Q&A session with our panelists. I'm sure you have some burning questions for them, and we see that some have already come in. Thank you for that. Now is a good time to put the rest of your questions into Teams. Let us know. What questions do you have for us? And while we wait for some of those other questions to come in, let's go into our last live poll. For those of you that may have joined since the beginning of this call, the way that you can join this live poll is by scanning the QR code on your screen. You can go to slido.com and enter the code USGS, or you can click the link that will be in the chat momentarily. And in this poll, we're asking you, how does the new water cycle diagram make you think differently about water? I think one of the most obvious components for me as I look at this diagram is that humans are represented in this diagram, whereas they weren't in the previous diagram. And that's a big step. It's a big change. It aligns with current science, and so it's appropriate for us to make that shift. On social media leading up to this event, we've shared some water cycle stories, and we're interested to hear some of yours, and that's kind of what this question's getting at. But if you end up wanting to contribute something before we have to move on, you can always use the hashtag #WaterCycleStories on social media to let us know what your water cycle story is and how this new water cycle diagram makes you think differently about water. And we're seeing some answers come in, and here's what they say. The importance of human influence, human interaction. It allows us to think about the human impact. Water is awesome and amazing for my 6 and 7-year-olds. It makes me think about how humans are involved in the water cycle and where water really goes. Someone loves Drippy. The new diagram helps you better connect to the planet's water. It's really interesting how groundwater can be young or old. It's super interesting, isn't it? The age of groundwater? Who would have thunk? Water extractions are better represented. De-emphasizing the giant arrows can help students understand that it's not just one huge infinite cycle, but rather multiple interconnected and nested cycles. Yeah, for sure. Less of a big cycle, more nested cycles. Highlighting the connection between groundwater and surface water. Yeah, really like how it makes you think about the anthropogenic aspect of the water cycle for sure. Showing several watersheds. This person says they've never had such a comprehensive understanding of the water cycle or how human behavior can impact the cycle. Well, thank you so much. We really appreciate that compliment. We understand that you are thirsty, and it's such a blessing that we have water, isn't it? It's a very good thing that we have water to hydrate us. Makes you think about the transport from water's perspective, for sure. We like the inclusion of agriculture, public use groundwater wells, as well as the addition of recharge flow patterns, different types of watersheds. Yeah, and I see people are still typing, and I just want to add something that comes to my mind as I read one of those last comments. You know, there are so many details to this diagram that Haley definitely started to walk us through, but I want to acknowledge that there are so many additional details that we can't wait for you to explore as you see the diagram published online on your own now. So we can go ahead and move into the Q&A section of today's event. I am proud to reintroduce all of the panelists who will be available to answer your burning questions. To remind you, Andy Creighton is a USGS hydrologist with the Colorado Water Science Center, whose research focuses on geophysics and snowpack dynamics. Marty Briggs is a research hydrologist with the USGS Water Mission Area Hydrologic Remote Sensing Branch. He specializes in understanding how groundwater and surface waters are connected and how groundwater influences stream water quality and habitat resilience. We are also joined by Jon, who is the surface water specialist for the Maryland Delaware DC Water Science Center, one of the many roles he has filled during his 30-plus career with the USGS in Maryland. We are also joined by Marina, a physical scientist at the same Water Science Center, and she studies fluvial geomorphology and remote sensing, primarily within the Chesapeake Bay watershed. We have Kelly Warner with us, the Deputy Director of Science for the Central Midwest Water Science Center. She manages the water science studies for the USGS in Illinois, Iowa, and Missouri. We have Emily Reed, the Web Communications Branch Chief within WMA of USGS, who has overseen the redesign of the water cycle diagram. And of course, we have Haley, the lead designer of the new diagram, and Rachel, our usability specialist. All right, let's start with some questions. Let me grab one of those questions. Great. So the first question that came in was, are companies allowed to display the new diagram on their website if the USGS is cited? Emily Reed, would you take that question for us?
Yeah, I'm happy to. So yes, the new diagram is in the public domain, meaning that it's not subject to copyright. So the diagram is open for anyone to use for whatever purposes they have, but I will say that we would always appreciate being credited as the source of the diagram if you're willing to do so, but it's not required. Thank you.
Great. All right. Thank you, Emily. The next question is for Andy. How many times do you measure the snowpack during a season?
That's a great question. It actually depends. So the Forest Service maintains a lot of permanent monitoring stations below tree line. They're called SNOTEL for snow telemetry. They transmit constantly, and those are going all of the times. They're wonderful. We have also been working on developing our version of SNOTEL that's above tree line. And those measurements go out every 15 minutes. It's amazing. We get to see what's happening on the ground in near real time, but at only one point. So if we want to understand what's going on a larger spatial scale, that happens about once a month that we go out and take those spatial surveys for snowpack dynamics. So 1 point every 15 minutes, larger spatial scale once a month.
Great. Thanks, Andy. Okay. The next question is, will we be able to purchase a large printout of the updated diagram? Charlotte, would you like to take that question?
I'd be happy to. So the print poster version of the diagram will be available for everyone to download for free at the USGS Water Science School website. So please just navigate over to that website after this release party and you'll be able to download a print poster version for free.
Great, thank you. All right, the next question is for Kelly. How does the quality of water downstream from water treatment plants affect the habitat and biology within the area?
Well, I wanted to thank whoever asked that question because it's always, I love it when there's a water quality question. And you'll probably hear a lot of the scientists saying, well, it depends, because it always does on the particular situation. So it depends on the water treatment plant. How big is it? What percent of the discharge from that water treatment plant makes up the amount of water in the stream? And then, of course, what is the quality of that water coming in from the treatment plant? And in these situations, we really have to look at each individual situation to look at the habitat and the biology downstream from the water treatment plants. And we do that. We have a lot of work going on in the USGS and ecosystems looking at fish and habitat and the water quality coming out of the treatment plants. And I'm in Illinois, and so we look, Chicago has some of the biggest wastewater treatment plants in the world. And they have a lot of, they do a lot at those treatment plants to treat the water and make sure that when it's discharged, it's the best water possible. So we come in and we look at the USGS, at the fish, at what changes in those habitats near those treatment plants. So it all depends, once again, on the particular treatment plants and on the conditions in the stream.
Great, thank you, Kelly. The next question is for Andy. How much of the snowpack melts on average for a season? In inches?
That is a great question. That depends on where you are. Different areas within the US get different amounts of snowfall. If you are a skier, you might get that, given that, you know, the Sierra Nevadas in California, the ski resorts there don't open up until January, February. They don't, or at least they don't get good until then. Versus out here in Colorado, our ski resorts open around Thanksgiving. So it really depends on where you're at, what type of snowfall you got that year, and which relies on climate. So are we in an El Nino, a La Nina? Are we experiencing a low snow, a typical snow, a high snow year? But more importantly, I think than the amount of snow we get is how does it melt? Are we experiencing a low and slow or a fast and high snow melt? And that really impacts how our reservoirs are replenished. So basically, this is an incredibly complicated question that no one has a great answer for. I cannot predict that for you. But what we've seen in the past is that typically snowpacks are being reduced, stream flows are being reduced, reservoirs are being reduced. Yeah, that's kind of where we're at right now.
Thanks, Andy. The next question is also for you, Andy. How has the use of drones affected avalanche safety?
It's new. So this is actually a really exciting moment for us. So currently, a lot of avalanche monitoring is done on the ground, digging snow pits, doing stability tests where you dig a core into the side and you slap it with your shovel and see how quickly it falls apart, and that's how likely things are to avalanche. It is what it is. This is the state of the science. However, as we develop more advanced technologies, including software-defined radar, even ground-penetrating radar, to look at the snow stratigraphy and being able to identify layers of instability, and then applying that to drones, where we can fly it and we don't have to send people into the areas where they might end up in an avalanche. It's wonderful. It's still being developed right now, but I am very excited for the potential to not have to send human beings, people, into the danger zone to determine avalanche potential. And this, I'd like to clarify, is not just for backcountry skiers who want to go out and ski, whatever. This has huge implications for highways in Utah, Wyoming, Idaho, Colorado. We hire people to go out and forecast these avalanche statistics so that we can close those highways. We can keep the motorists safe. We can do avalanche mitigation with explosives when we feel that it's necessary. So I think there's so much opportunity when we don't have to send people out into those areas.
Yeah, that makes a lot of sense, Andy. Thank you for answering that question. It definitely makes sense how using drones can ultimately prevent people from having to go into the field to do those very things. So of course it's going to enhance the safety of those individuals. Thank you. The next question is for Haley. The question states, many states lack mountains. Snowmelt is all over in states with cold winters, and Great Lakes states have large bodies of water before draining into the ocean. Should that be reflected in the diagram?
Thanks. That's a really great question. You're absolutely right that those sorts of environments aren't depicted here. We were not able to depict all different environments. And in this case, we chose to highlight mountain snowpack because, as Andy noted, it's so important for water supplies in the Western United States. However, what we hope is that by showing a variety of environments, that anyone across the country or even across the globe will be able to identify with certain parts of the landscape that are depicted. So even if we're not able to show really, really large lakes like the Great Lakes or snowpack on like the Midwest plains, we hope that you'll be able to see yourself in this diagram and understand some of the hydrology as it relates to where you live.
Great. Thanks, Haley. The next question is for Charlotte. Will this be translated beyond English and Spanish?
What a great question. So as we mentioned before, our current diagram is available in more than 60 languages, and many of those translations were done by users of the diagram. So while we're initially releasing this diagram in English and Spanish, our expectation is that it will be available in many more languages over the years, including translations done by end users. So get in touch with us if you're interested in assisting us in this endeavor.
Yeah, and how would users be able to contact us if they wanted to get in touch with us about that?
They can email the USGS Water Science School team at water-science-school@usgs.gov, which we'll put in the chat.
Great, thanks, Charlotte. The next question is for Haley. Is saltwater intrusion into freshwater groundwater systems represented in this diagram?
Yes, it is. That was one of the things that we wanted to be sure to depict in our groundwater representation. If you look here where it says water cycle on the diagram and look above it, you'll see where 3 different aquifers meet the ocean. The bottom 2 have natural unaffected saltwater wedges that extend into those aquifers. But then the top one, which has a pumping well near the coast, you can see how that well is actually pumping at a high enough rate that it's pulling salt water up into the freshwater aquifer. So yes, we do include that, and we really wanted to show it because it is such an important water quality issue in coastal areas.
Yeah, that makes sense, Haley. We have another question for you, Haley. What was the reason for not labeling the cone of depression in groundwater?
That's a good question too. You know, there were so many features all across the diagram just like that we would have loved to be able to label, because we really did include so many details in this diagram. But from a design standpoint, if we labeled all of those interesting features, the diagram would just be covered in labels and it really wouldn't be useful. In addition, we wanted to limit labels to key pools and fluxes. And the cone of depression itself is more of a result of human impact and human use of water than a flux itself. But that sort of thing is exactly what we're going to be able to highlight on new content on the Water Science School, where we can really dive into more details, provide smaller diagrams or close-ups of the diagram, and really speak to those impacts of human use and other details that are shown in the diagram.
Yeah, that makes sense. You have to choose, pick and choose. There's another question for Andy. Which provides more accurate data, GPR or drone?
That is a great question. As of right now, ground penetrating radar has been proven to be accurate with in situ measurements. In situ meaning in the ground measurements. So we have these direct measurements with ground penetrating radar measurements, and they match. So from there, the USGS is building upon drone technology. So we're working on in the air technology and correlating that with on the ground radar and in the ground direct measurements. This hasn't been fully sussed out yet. We're still working on this. It's wonderful though, given the potential for this work. So the question being, which is better right now, on the ground, eventually in the air?
Great. That's a pretty succinct answer. Thanks, Andy. The last question that we're going to ask tonight before we announce our raffle winners is for Haley. Do closed basins contribute to groundwater recharge?
That's a really great question, and that's another situation where it depends. It depends on the geologic history of that basin. In many closed basins, there's this really, really, really deep layer of sediment, and sometimes there is groundwater within those sediments, sometimes really big groundwater aquifers. However, that groundwater aquifer is not always fed by current hydrologic processes. Sometimes that groundwater is present because of really, really long ago. So for example, in the Harney Basin in Oregon, groundwater there is present because the area actually used to be a massive lake. But nowadays, although there is groundwater recharge that comes in from snowmelt and other areas in the basin, it's actually very small compared to the amount of groundwater that's there and the amount of groundwater that's being used. So in that case, while the closed basin can contribute groundwater recharge, it's not necessarily a large amount. But ultimately, it depends on the geologic history of the basin and what pathways there are for groundwater to recharge.
Thanks, Haley. Great. All right, so let's have our closing remarks and then we will announce the winners of our raffle. So I just want to say thank you so much for joining us for this historic release of the new water cycle diagram. We are so excited to share this new diagram with you all. The new diagram re-envisions the water cycle with human impacts at the forefront and provides a modern update to maximize scientific accuracy, design, and usability in educational settings. This update encourages a new way of teaching and understanding water so that we acknowledge the power humans have to affect the world we live in. We hope today has inspired you to see your own water cycle story. Share your water cycle stories with us on social media by using the hashtag on the screen, #WaterCycleStories. Email us with any questions at water-science-school@usgs.gov. This event has been recorded, and the recording will be available on the USGS YouTube channel and on the Water Resources Mission Area website within 1 to 2 weeks following this event. Okay, are you ready to know who the winners are? I'm so excited to share this. Ian Y, Hannah D, Adiona K, Gwen V, and Emily S. You have won the new water cycle diagram in poster form, 38 inches by 26 inches. It's going to be yours. We're going to email you. Don't worry, we'll find you. We're going to mail you this new diagram. We hope you are as excited as we are. Thank you so much for attending this event. This event is over. Have a great night.